Welcome to the online lecture on numerical methods by Professor Tanuja Endate from Electrical Engineering Department, K.K. Wag Institute of Engineering Education and Research, Nasik. This is the syllabus for second year electrical engineering, in which we study various numerical methods. We understand that there are different types of equations. The equations could be linear. Linear equations can have single variable or multiple variable. For example, if 3x minus 4 equal to 0 is a linear single variable equation and 2x plus 3y equal to 4 is a multivariable linear equation. The equations which represent a straight line are called as linear equations. There could be nonlinear equations which are called as polynomial equations. They could be in single variable polynomial equation with higher degrees of higher powers of one variable. So 3x raised to 4 plus 4x cube minus 2x square plus x equal to 4 becomes the example of a nonlinear equation. It is a polynomial type of single variable equation. The nonlinear equations can also be of transcendental type. Transcendental equations include trigonometric equations, logarithmic equations, or exponential equations. The equations which include any of these terms along with other variables are called as transcendental equations, which are necessarily nonlinear equations. The examples are sin x minus 3 equal to 0 is a trigonometric term, and so it is a transcendental equation. X plus log x equal to 2 includes the logarithmic term, whereas 3 plus e raised to x equal to 0 can be the example of term which includes exponential. In this, we also study some differential equations. Differential equations are called as ordinary differential equations. They could be linear, which are first and second order equations. If it is dy by dx equal to 2x plus y, they are considered as linear differential equations. Second order equations can be written as d square y by dx square plus x dy by dx minus 3 equal to 0. Now, to obtain the points which satisfy these equations, we call them solutions of algebraic and transcendental equations. We have already studied Descartes' rule of sign change, which helps us identify the possibility of positive and negative real roots of the given equation. Similarly, we have also studied intermediate value theorem, which tells us that for a continuous function between a and b points, there lies a third point which necessarily can be the root of this equation, provided the function changes its sign between a and b points. So, when we start solving these equations, we usually have iterative methods which are adopted for solving these equations, and so we need to start with some initial guess values. If we require two initial guess values around the possible root, then it is called as a bracketing method, and it guarantees the convergence. Since the starting values are surrounding the possible root, they guarantee the convergence. The methods which are bracketing methods, are bisection method and regular falsi method. They require two initial starting values guaranteeing convergence. Whereas the other type of solutions methods which are available, they are called as open-ended methods. So open-ended methods need one or two starting values which may not envelop the root, and so the convergence of these methods is not guaranteed. The examples of open-ended methods are secant method and Newton-Raphson method. In numerical methods, we are going to study all these methods. Okay, and today we will be focusing on Newton-Raphson method. Now, Newton-Raphson method is a method its expression is derived from Taylor series expansion by considering only first two terms of the expansion. And so if we start with the initial guess value, it requires only one initial starting value, say xn. If we take xn as the initial guess value, we need to evaluate the given function at this point, so which is fxn. Now at the same point, if we draw a tangent to this point, the slope of this tangent is denoted as f dash of x. This slope evaluated at xn point we can write as f dash of xn. If we use these two values, f of xn and f dash of xn, for giving correction in the approximate starting value, we can find a point which cuts the x-axis by using the slope of the tangent. So xn plus 1, which is a new value, can be evaluated by using slope of this tangent, which is y/x, and so slope can be calculated, and using this slope we can evaluate xn plus 1. Since we are assuming this to be a root value, we assume that function at this point ideally should be 0. If this is a root, the function should take 0 value. Okay, with this assumption we can rearrange the expression and we can obtain xn plus 1 like x1 equal to xn, the initial value, which could be x0 as well, minus function evaluated at the starting point, which in this case would be fxn divided by f dash of xn. So if we use f of xn divided by f dash of xn as the correction in the initial starting value, we can obtain the new value of the root. Now this process is surely iterative, because if xn plus 1 is required to be the root, the function needs to be 0. Function value needs to be 0. But actually we can now again evaluate the function at this point, repeating the process, draw a tangent at this point to this actual function, calculate slope of this tangent as f dash of xn plus 1, and where this tangent line cuts the x-axis, assume that this is the new value of root. So xn2 plus 2 can be evaluated in terms of xn plus 1 minus fxn plus 1 divided by f dash of xn plus 1. This continues again at xn plus 2. We can evaluate the function value, we can draw the tangent, we can evaluate the slope of the tangent, and where the tangent cuts here, now we can realize that as compared to the initial starting value, we are gradually moving towards the actual root, which is the cutting of this function line with x-axis. Okay, so this process by which we converge on the root, okay, is ensured if we have Newton-Raphson method. Now this rate at which this conversion takes place is very fast in case of Newton-Raphson method, which makes it extremely popular. To go ahead, we can just know a little more about Newton-Raphson method. That is most widely used root solving method, and when it converges, rate of convergence is quadratic in the sense the convergence rate is 2, whereas bisection method is considered to have linear convergence. Again repeating, bisection method is a bracketing method, so it ensures the convergence, whereas Newton-Raphson method starts with only one starting value. It's open-ended method, so it does not guarantee convergence, but when it converges, the rate of convergence is 2, quadratic convergence. Now these are steps where we take initial starting value as x0, then we evaluate fx0 and f dash of x0, we make correction in the value of x as x1 equal to x0 minus fx0 upon f dash of x0, and then repeat the process. We check the convergence in the sense we have to keep on checking the value of fx0. When fx0 becomes 0, we can say that this is the root value. Okay, this is how Newton-Raphson method can be used. Now let us understand by solving a problem. Suppose the given equation is x cube minus 2x square plus x minus 3, and we have to start with initial value as x0 equal to 4. So first we take the first derivative, which is slope of the tangent, and in general form the slope is calculated, the function derivative is calculated as 3x square minus 4x plus 1. Now when we start evaluating for x equal to 4, we put this value as 4, evaluate the function by putting x equal to 4, its value comes to be 33, and the first derivative evaluated by putting x equal to 4, we get the value 33 again. So both these functions are getting same value, and so from 4 we get the new value as 3. 4 minus 33.33 becomes 3. Now we evaluate the same two expressions again by putting x equal to 3, and we get new value x2 calculated from x equal to 3 value. So x equal to 3, function evaluated by putting x equal to 3 becomes 9, f dash of x1 becomes 16, and the new corrected value is 2.43. Now you can realize that as the function value keeps on reducing, we are sure of convergence because it is not diverting, it's not going away from the root. Okay, so gradually whenever we evaluate this function, its value should be moving towards 0. You can realize here 2.03 is the function value for the third iteration, and at the end of third iteration we get the new corrected value as 2.213. So since we are asked to calculate for a number of iterations manually, we can stop the process here, but we are confident that it is converging because looking at fx0 value, it is continuously reducing, it's moving towards 0. So next time when we put this value, I am sure function value will be further reduced, indicating the convergence of the process. Let us take one more example. If fx equal to 2x cube minus 5x plus 1 equal to 0, using Newton-Raphson method, initial value of x is 0, show 3 iterations. So first we evaluate the first derivative, f dash of x equal to 6x square minus 5. Now put x equal to 0 and evaluate, function evaluated becomes 1. This f dash of x evaluated at x equal to 0 is minus 5. The correction in value is 0 minus 1 upon minus 5. Okay, so new value becomes 0.2. Moving further, we evaluate the function at 0.2. We evaluate the first derivative at 0.2 and we get these two values. The new corrected value of x2 becomes as 0.2032. And continuing this further, at 0.2032 you can look at the function value. Earlier it was 0.016, now it is 0.0078. So it is surely moving towards 0. And so at the end of third iteration we get this value as 0.2048, ensuring the convergence of the process. Just for ensuring, if we put this value into function again, the function value is now 0.0068. Now you can see 0.2032, it is 0.0078. At 2048, it is minus 0.0068. So it is between these two values. The actual root may be 0.2032 and 0.2048, possibly somewhere in between. Okay, so further approximation we can easily say it is between these 2 points, and we can take it as 0.204. Okay. Since these are all iterative processes, we have to stop after number of iterations looking at the function value. Now, though Newton-Raphson method is very fast in converging, it does not guarantee convergence, and in certain conditions the Newton-Raphson method fails to extract a root. So these are some cases where we can realize that Newton-Raphson method fails to converge. Okay, the first case we can say this is called as a reflection point. Now if we start with x0 as the starting value, and we continue with the process. The tangent meets x-axis somewhere at x1 and we evaluate the slope again. Now this is getting us x2 point. Now if we see at x2 point, this again meets at x1 point, and this process appears to be a loop where x1 and x2 values will keep on repeating themselves without actually converging on this root, which is a real root. Okay, so this is a case where Newton-Raphson method may not be converge and give this actual root which is between this point. Okay, so this is one of the failure cases where Newton-Raphson method fails, and it is called as a reflection point. The second case is oscillating around a local optimum. Now if the function is of this kind and we start with a starting value, say x0, then we take a tangent, okay, we calculate this point, again we converge on x2 point. So first we go at x1 point, we calculate this value, take a slope, we converge on x2, again we take a slope, we converge on x3, take a slope, converge on x4, and so on. But it keeps on oscillating at these points because it is just around a local optimum. This point we may not be able to converge, because at that point when we calculate the slope, it becomes parallel to x-axis and indicates zero slope. So that tangent line will never meet the x-axis, and so it will not be able to give us root if the function is of this kind. Okay, so this is one of the failure cases. We cannot predict this beforehand, okay, because we are just taking one starting value and beginning the process. And the last case, which is shown here, is called as zero slope. As we indicated, I skipped this point. Third case is near zero slope. So when we start with x0 point, slope of this line is very close to zero slope. So that line would be almost parallel to x-axis, and so it will go far away from the starting value. You can see here x1 and x2 will be somewhere very far away, because these lines which we have shown in the diagram, they have not shown very parallel to x-axis, but their slopes are very small, so very near zero slopes, and so these lines are almost going parallel to x-axis. In such cases, the method will fail. And the last case, where actually the slope is parallel to x-axis, where the slope is 0. So we start with x0 value, it converges on x1. At x1, when we calculate slope, it becomes 0, and so it fails to meet the x-axis anywhere, and so then it will not be able to identify any root. So these are some of the cases at which Newton-Raphson method fails, but rest of the times it is considered as very fast converging method. It requires only one starting value, so very easy to adopt, and very less calculations because only evaluation of function and first derivative is required. So Newton-Raphson method is extremely popular among all the methods because of these advantages. So when we compare the iterative methods, we have bisection method, regular-Falsey and Newton-Raphson method. Considering their nature, bisection method is bracketing type, regular-Falsey is also bracketing type method, but Newton-Raphson is not a bracketing, it is open-ended method. Initial values needed, bisection, whichever are bracketing, they always require two starting values, whereas open-ended method can start with one value. The rate of convergence of bisection method is only 1. Regular-Falsey has higher rate of convergence of 1.6, but Newton-Raphson considered to be fastest because it is having rate of convergence as 2. Guarantee of convergence for bracketing methods, the convergence is guaranteed, but it is not guaranteed in case of Newton-Raphson method. And the speed of convergence of bisection method is considered to be the slowest. Regular-Falsey has medium speed, whereas regular Newton-Raphson is considered to be the fastest converging method. Okay, so with this we can just check whether we have understood whatever has been taught in this lecture and try solving these practice problems. First question is for regular falsy method. Second question is for Newton-Raphson method. Then the third question is you have to solve by both methods and compare the results with each other for same number of iterations. Okay, so that their accuracy of result and nearness can be checked by comparing same starting value and same number of iterations for such comparable methods. I hope you have understood. Thank you.